everyone, it's Anirudh from 61B, and today we're going to be talking about the Spring 2020 final, specifically question number 7. So this one has to do with LLRBs, specifically a 2-4 tree, at least to start with, and we're going to go ahead and try to determine what this 2-4 tree drawn up here is going to look like if we represented it as an LLRB, right? So let's go ahead and get started. We'll be using nodes themselves as being colors, right? So if you're in a future semester where you're using an edge as a given color, you can sort of translate it as being, if I have some edge between two nodes being red, it's the same thing as the node that is like below it being red. So, right, so if I had something like A and B with some red link between the two, that is the same thing as B and A. So the second one is easier to code. The first one is at least for me, a little easier conceptually to think about. But for just the sake of ease, I guess, and also because I've become used to doing it, I want to be using this second one, but I wanted to put this in here in case someone from the future is watching and you're wondering what this notation is about. Okay, so if we have multiple things that are within one given node, right, we want to go ahead and sort of think about breaking it apart into multiple things. So this 10-4 is going to sort of become this 10 node up here. And then we're going to go ahead and create a 4 node over to the left, right? Whenever we can, we're going to try to lean toward the left, right? If we have the choice between leaning toward the left or leaning toward the right. If we don't, then we just have to create 2. But if we have that choice, we're going to go ahead and pick going to the left. So we have a 1-to-1 mapping between any given 2-4 tree drawn out as like a B tree representation versus our LLRB. Okay, so we have our 10-4, and now we're going to go ahead and add in our 2 over here. Let me go ahead and make this a little bit bigger. Okay, and then we're going to go ahead and add in our 8 and 6. So very similar to before, we're going to go ahead and add our 8 over here. But then to join in our 6 with our 8, we're going to go ahead and add it in as a red node. And then we're going to go ahead and add in 12, 14, and 16. So remember that we choose left leaning when it's possible. In this case, it's not possible. So we're going to go ahead and set 14 up here to be a black node. But then we're going to go ahead and create, I'll go ahead and create 12 and 16 as red nodes, and then we're going to connect them, right? And so we didn't have a choice here, so we can go ahead and create one on the right because there's already one on the left, right? The idea of the left leaning red-black tree, like I said before, is when you have the choice, you'll try to go left. So this sort of draws out our tree, and somewhat quickly, I'll actually go ahead and start filling this in, right? So our A is going to be 10, right? That's our very root tree. Our B is going to go ahead and be 4, and it is indeed red. C is going to be 14, and it is not red. Then we're going to go over to D, which would be 2, and we notice that it is not red. E is 8, it's not red. F is, I believe, 12, which is red. Right, and then G is 16, which is red. And then notice that we don't have an H or an I, right? Because the H or I would go somewhere here or here, but we don't have anything. Instead, we just have a 6 located where the J is, right? So we have a 6 that is red where the J is, right? So this is, I guess you could draw it here if you want to really try like annotate it, but I find it just very useful to go ahead and draw it out manually as a separate graph. Okay, let's keep scrolling. Now we go to B. We have a new kind of balanced search tree here. And we're trying to determine, well, what sort of tree could this represent, right? So before we had red-black trees, which we used to represent 2-3 or 2-4 trees. Now we're having red-black-green trees. Okay, well, you may not have seen this from lecture. In fact, I very much doubt you would. At least for this semester, we didn't do it. But the point of this question is to see how well you understood the ideas of why we even have red nodes to extend, right, into how they would be applied for red-black trees. And so we give you a list of conditions, right, that must be satisfied, or you can think of it as like invariants at any given moment for these kinds of nodes, right? So the root is black, empty nodes are considered black, right? So it's kind of very similar to the idea that we had previously, right, where we start with 10 being a black node, and then all of these little leaves here are like empty, right? They're like just like our like final concluding points are treated also as black. Then we have the number of black nodes in any path from the root to the leaves are the same, right? So that number of black nodes denotes like how many actual levels we have, right? A black node may only have black and red children. A red node may only have black and green children, right? So we go black, then red, then green. We never go black directly into green children. Green nodes can only have black children. So we can't go black, red, green, red, and then alternate between the reds and the greens, right? So it's like we go black to red, then possibly to black, or we go to green and then we go to black, right? So it's like we have the option of adding one more layer. Okay, and then except for null nodes and possibly root, all black nodes must have at least 2 red children. Okay, interesting. So let's go ahead and look at this. So like red-black trees, which trees correspond to a kind of B tree, which kind? So remember the way that we define B trees, right, is, or at least for red-black trees, red-black-green trees, is we think about if we have some sort of black node up here, we think about how many black nodes we can represent, right, at the next layer, right, and we want to sort of maximize the number that we can fit in, right? This is like the idea of like stuffing in the node by using these other colors. So let's say I have 2 red children, and then I had 2 green children, right? Remember that it's still a binary search tree, right? So I have something that looks like this. Well, how many children can I fit in here? Let me go ahead and actually move this down all the way over here. What I can do is I can fit in 1, 2, 3, 4, 5, 6, 7, 8. Right? So that's 8 possible children that I could fit in, right? So that's my maximal case is 8. What is my minimal case? Well, maybe my minimal case is just I have 1 black node and then 2 more black nodes, right? But, well, for one, this is impossible, right? You can go back to the regular red-black trees and realize why this would never be the case, right? We always try to stuff, and then when something is overstuffed, we push up. But in this particular case, we're actually given something that is going to help us out a lot, like a lot, right? It's going to make our lives very simple, which is we know that every black node must have 2 children, except for null nodes, and perhaps the root, right? Like if we don't have enough people in the tree to start with, then maybe you don't even have 3, maybe you only have 2, well, then the black node wouldn't have 2 red children. But let's say you have a decent number of people, right? So then you go ahead and now you can branch out. And here you can go ahead and create 4 children. So in other words, it would be a 4-8 tree. Now, I think for me personally, when doing the question, I realized the 8 part before I realized the 4 part. And at least I think this is the only option that has an 8 as the second option, right? It's the maximal number. So that's how I would do the question, right, on an exam. But I think it's still useful to understand why there's 4 and why it's not 2 or 3, right? You have to represent 4 because you can't just have one black node going directly like you would previously. Okay, now we look at assuming a search tree meets the constraints in part B. Will it sufficiently balance that searching for value will require O log n time for a tree with n keys? Okay, so remember that the way that we think about balancing, right, is that we do these rotation operations and these color flip operations to maintain our left-leaning properties, which really help us with creating that balance. But the thing is that we impose these constraints as a means of justifying why we do those operations, right? So we do those operations to make sure that these constraints are always valid. So question is, do these constraints, if these constraints are held, then will it still require log n time? The answer is yes. It's almost the exact same reasoning as the red-black trees, right? The idea is just that we're just sequencing our nodes together in what we believe are clever ways to go ahead and try to distribute our data by stuffing as much as possible. Yeah, okay. And then this is like a side note, but it also shows why we use red-black trees and why we don't have 60 colored trees that we draw, right? Because it seems like if we're asymptotically going to get the same runtime, perhaps it's just easier to stick with the red-black trees that we know and we love from class. Okay, so that wraps up question number 7 on the spring 2025.